In the last video, I've talked about how we can use this potentiometer setup to measure the EMF of a battery. The way is to connect this unknown cell to a sliding contact with an ammeter in between, and then as we slide this contact up and down until and if we can find a point where the current goes to zero, then the voltage produced by across these 2 points between the sliding contact and the end point should be equal and opposite to the unknown cell's EMF, because that must be why the current here becomes zero. Now in this video, I'm going to talk about how to use the same setup to compare potential differences. Now let me explain what I mean by that. Okay, suppose that I have a circuit. I have another circuit with, say, some battery here with an unknown voltage connected to two resistors. Okay. Now, one of the resistors has a known resistance of, say, 10 ohms. But the other one, the resistor of the other one, is unknown. So I don't know this voltage, I don't know this resistor. This one is all I know, right? Maybe I bought this resistor myself and I know that it's 10 ohms. Now what I like to do is to use this setup to find this unknown resistance. Okay, let's see how I can do that. First, I shall connect this point to this point with a wire. Okay, and then I shall right, maybe before I actually connect them, let me briefly explain what I'm hoping to do before it gets complicated. The idea, right? The idea is this. In this battery, okay, although we don't know much about this circuit, we can still think of the relations and the equations relating the resistance and the voltages across them. Okay, now so suppose that the resistance across here is, I call it V3, across here is V4. And suppose that the current going through here is I2. It's I2, right? Okay. So now, okay, maybe we don't need I2 because we already know about the idea of potential divider. We know that the ratio of these two voltages must be the same as the ratio of R to 10. Okay, so let me write that down. And that actually is the idea that I want to use. V4 over V3, the ratio of the two voltages, is equal to the ratio of the two resistances, R over 10. Alright, so this is something that we understand from what we learned about potential dividers. And what I hope to do using this potentiometer is that I hope to find this ratio. I hope to find a ratio between those two voltages, because if I know this ratio, then I can calculate R. I want to find this ratio. Now that doesn't look any easier, right? Finding these two ratios. But if you recall the previous video, the previous video was about finding the EMF of an unknown cell using this setup. Now if I can find the EMF, I can find an unknown voltage like V3. So if we think along those lines, it might not be so difficult after all. So let's try this out. Let me start by using, or at least trying to use, the method in the last video to find this unknown V3. I know that I should be able to do that. Now, I would therefore connect this to this point. And what I'm going to do is, you remember that in the last video, I talked about finding an unknown EMF of a cell. Now this time, V3, or rather this 10 ohm resistor, is not really a cell as such. But I can imagine that because that there is this voltage V3 across the 10 ohm resistor, the 10 ohm resistor can act like a cell that produces this V3 voltage. So if you think of it this way, we can think of this resistor as if it is a cell and we want to measure its resistance. Okay, it's not really a cell in itself, but it got this voltage from the circuit that's connected to this cell. Alright, but we can measure it just like we measure the EMF. And if we treat this like the unknown cell in the last video, that means that I should connect this to an ammeter. Okay, should connect this to an ammeter and then to a sliding contact that just touches this long resistance. And I should slide this along here until I reach a point where the current here is 0. Okay, and if you remember, this is possible because I have the positive pole here and I have the positive pole here, current flowing this way, and it means that this point has a higher voltage than this point. That point has a higher voltage than this point. The current flows down here, and therefore these two points, these two resistances act like batteries that try to drive currents against each other in opposite directions. So if I slide this up and down until the voltage from here, which I'll call V2, is equal and opposite to this voltage V3, then the current would be 0. Okay, and remember also that this V2 voltage is directly related to this length. I'll call this L2. Okay, V2 is related to L2. Now let me quickly write down the reason again. Because it's related through the resistivity equation. V2 is equal to IR, where I is the current through here, R is the resistance of the whole piece. Oh no, wait. R is the resistance of this bit here, which I call R2. Just this bit, R2. And then just here, the R2 is in turn related to the length L2 by the resistivity equation, big L, where L is the full length of this wire. So R2 is proportional, therefore R2 is proportional to, V2 is proportional to R2, R2 is proportional to L2. Okay, V2 therefore is proportional to L2. Now from this connect on this side, let me take a look at what happened. Take a look at this side here. On this side, we know that the voltage across here is proportional to the resistance. Okay, and since this voltage will become equal to this voltage will become equal to this voltage, it just means that this resistance will become proportional to this length according to this setup. So if I call this resistor, okay, I should give a name to this. If I call this resistor R3, then it means that R3 is proportional to V3. R3 is proportional to the V3 here, and V3 is equal to the V2 when the current here is 0 ampere. I adjusted this until the current here is 0 ampere, and V3 then would be equal to the V2, and V2 is proportional to the L2. Okay, so therefore it means that the R3 here is proportional to the L2 there. So with this condition that the current here is adjusted to 0, the resistance here becomes proportional to the length of this bit. So it means that if I want to measure this resistance, or if I want to find a ratio between these two resistance, what I could do is I could find this length L2, and then I can take out those two connections and connect these 2 points across this unknown resistor, and slide this again until the current is 0, and measure the new length. Okay, then the ratio of the new length to the old length would be equal to the ratio of the two resistances. So here's the plan. So let's actually try this out. Need to clear this knot first. So previously I've connected, when this was connected to the 10 ohm resistor, I had the L2. So let's say the length here, that corresponds to let me draw it out again, just to make it very clear. So first I connect. This is the procedure. First I make this connection. Connect this to an ammeter, and then to a sliding contact here. Okay, then I would measure this distance. I would measure this distance, L, which I call L. and so when these 2 points are connected to the 10 ohm resistor, the L there, let's say the L there is 0.2 meters. Okay, let's say when I have to adjust this until this length is 0.2 meters, then I'll get 0 current here. I'll get the 0 ampere down here. So this is the first measurement. Okay. Now what I then do is this. I would let me clear this up first. I would remove those 2 wires. Okay. I should still write down my previous results when I had the 2 wires connected across the 10 ohms. The balance, meaning where the connected current is 0, is achieved when the length of this section is 0.2 meters, right? That's what I said. Now, then I would take out those 2 wires and connect them across this unknown resistor. So the other end will still be connected to the same, well, one end to the same point at the end of this long resistor. The other end connected again through an ammeter to a sliding contact. So I will slide this up and down until this is again 0 ampere. That's where the 2 voltages are balanced. The 2 voltages here and here. Then the length here, suppose that the length here is then, when this is connected to R, suppose that the length here is now 0.3 meters. Okay. So since we know that the voltage across here is equal to the voltage across here, and the voltage across here is proportional to this length, okay, therefore the ratio of these 2 resistances must be equal to the ratio of these 2 lengths. So now I have what I need to calculate. Okay, this result tells us now that R over 10, this ratio must be equal to this ratio, which is 0.3 over 2, 0.2, which is 3 over 2. Now, earlier in the video, we have seen that R over 10 is also equal to the ratio of the voltages. That's what we understand from the potential divider idea. And it was this, right, and that these voltages are proportional to the length L across here when this balance is achieved. And this is what gives us this connection. What tells us that these 2 resistance from here must be proportional to the length here. Or each of these resistance must be proportional to the balanced length, meaning the length where the current is 0, where the voltages are balanced. So with this equation, R over 10 is 3 over 2, we can obviously calculate R now. So just bring the 10 over and multiply both sides by 10, and we'll get 2 and 10 cancel to give 5. 5 times 3 is 15 ohms, and that's the answer. That's the answer. So in this way, we can, what we have actually done is we have compared the potential differences across those between those 2 resistors, right, which is V4 over V3, and we could compare them because each of these voltage is equal to the voltage across this resistance when the voltages are balanced, and the voltage here is in turn proportional to its length.